Easy experiments.
Pendulum.
Pendulum, yep. Next week you will do the physics experiments.
Okay.
In Stephen's lab, in the classroom. Huh?
With A4.
Yeah, something like this, yeah.
In the last time.
Yeah. Oh, you did them last time.
Yeah.
So you remember them?
Yeah.
So you can help them? Yeah.
Difficult.
No, difficult.
Yeah.
Example
Yes. Be careful here. Okay. Now, have you got the questions open there? We can have a look at them. Alright. Okay, hang on, let me open up the questions.
Too large. What is too large?
Too large? What are you talking about?
Something in English.
Maybe my mistake. Hooke. Easy or difficult homework? Oh, good. I'm glad.
Maybe.
Maybe what?
Maybe both.
Oh, maybe so. Alright. First question. A piece of rubber has a constant of 5. How far has it been extended if it's offering a restoring force of 20 newtons? Okay. So here, come on, broken. Whoop. Hang on. Sorry, my pad is breaking. Well, I'll just... Oh, here we go. Okay, so the first one, K equals... Maybe it's time to get a new one. Yeah, no. I said maybe.
How much did you buy this one? Tablet.
50.
See?
I know, it's expensive. 50.
I buy a new one, it's less than
50? How much?
No, maybe 30.
Like this?
Yeah.
Where?
Amazon.
Okay, interesting.
New one.
Yeah, I'll think about it. Right, so what was the K? 5. And the F? 20. So you have F equals K delta X. So delta X is F over K, 20 over 5. What? I know. I'm too fast for it. 4 meters. You got this one? I hope so. Okay, number 2. Oh, I made a mistake? Oh, you didn't do it. Oh, I can understand. Yes, okay. Okay, number 2. What is the spring constant if it extends by 2 centimeters? Okay. And how big is the weight?
1 kg.
1 kg. And this causes an extension of 1 centimeter?
2 centimeters.
2 centimeters, okay. So then the weight here is 1 g. So this is the F. Or really, I suppose it's the same as the F here. So you have F equals K delta X. So the K equals F over delta X, which is 1g over 0.01, which is 100 g, which is 981. Is that right?
Wait, why is it 100 G?
Oh, divided by 0.01. Newtons per meter. Did you get that, Grace?
No.
What happened?
Your distance is 0.02.
Oh.
Yeah.
Delta.
Wait. Thank you. My bad. That's 200 G. What's that?
490.5.
419? 490? 0.5. Okay. 491. Are you sure?
Yes,
No.
yes.
No.
Yes.
No. No.
No.
Yes. Yes. Okay. Next.
Yes.
Okay. A spring is placed on the ground and a weight is placed on the spring. The spring compresses 3 centimeters. How much work has the weight done? Okay. It's so slow, I don't know why. Okay, what's the weight? 3 kilograms? What did I say it was?
Yeah, I didn't say.
You didn't say like.
Didn't I? Interesting. I don't need to say it then. Right, so this is a weight here. And how much has it been compressed?
3 centimeters.
3 centimeters. And what else do I tell you? Is that it?
Yeah.
No, I have to give you the weight.
No, baby.
Yeah.
A weight.
Good for English.
Yeah, great for English. We'll make it 10 kilograms. Are you sure I'll give it to you?
You can see.
You can see.
Then I need to give you something else. I need to give you like the K. So we'll make the K, I don't know, 100, no, too much, 10 newtons per meter. Okay, so I'll give you this. Okay. What's the work done? The formula is a half K delta X squared, or X squared. So that'd be 5 times 0.03 squared. Yeah? So that's 5 times 3 over 100 squared. So what's that? 9 times 5 is 45 over 0.0000. 1, 2, 3, 4. .5 millijoules. Yeah. Any other ideas for how you could do this one? Get the work done. Well, tell me this. Where did this 4.5 millijoules of work come from?
No way. Gravity.
Where did this energy come from, this work?
The ground.
There was work done here, and it came from the potential energy. Yeah? So, you know that the potential energy should be 0.0045. So that means mgh should be 0.0045. So now you can get the m. So the m is 0.0153 kilograms. You got that? Yeah? Now that I have the m, I could also work out the force. What's the force? Well, that's the weight, which is mg. So that's 0.15 newtons. But also, you can get the force this way. K delta x. What's the K? 10. K 10 delta x 3. Now, there's a reason why these answers are different. So I could use this formula. Oops. It's a bit of a delay. Or I could use this formula. So there's actually a big difference between the two answers for the force pushing down. I could use the formula for the weight, or I could use the Hooke's law formula. Why is it different? That's my question.
Because they're constant. I don't know.
Any ideas?
Because you should divide it 1 over 2.
Yeah.
So this force is just a push force.
You're trying, Andy, but not quite. I'll tell you which one do you think is the right one and which do you think is the wrong one?
The right
Right one.
is right.
No. In fact, this is the correct one here. And this one is nearly correct, but this is the thing. This formula, force, I suppose you could say work equals force multiplied distance. This force here is the average force. You see, usually the force, usually the force is constant, but in this example the force is changing. Is there more force from the spring at the top or at the bottom? Well, you see, when the spring is at the top, there's a small force here. But then when the spring gets compressed, there's a bigger force. But that's not the average force. The average force would be 0 plus this divided by 2, which is 0.15. And now it's the same as the weight. So this one here, that's a little bit too maybe difficult for the exam. But my point is, for this formula, the force is an average force. And usually it's constant, so it doesn't actually matter. Continue? Great. Okay, there's just one left, I think. Have a look. 4 people, each of 65 kilograms, sit in a car. The car reduces in height at distance 1.5 centimeter. The car has a mass of 2,000. The car reduces in height because 4 is press. When the people get out of the car wobbles up and down. What's the time here? So I tried to trick you a little bit here. There's a piece of information I gave you that you don't actually need.
The weight of the car. Right?
No. This you need. Not this.
The car has a mass of 2,000.
No, not this. You need this.
It's high.
Yeah, the 1.5. So what happens here, you have 4 springs for the car. This is my springs on my car. And I also told you the mass of the people, but I didn't need to tell you that either. Because what happens is the 4 people get into the car and come back out. And then when they come out of the car wobbles a little bit. So the car starts to move up and down. This is what happens. They get, when people get out of the car, sometimes the car wobbles a little bit. Yeah. You don't need to know anything about the people. You don't need to know how much the springs move. If you want the time for the wobble, you just need to know K over M over K. And the M is, now there's actually 4 springs, and if the car was 2,000, then that's 500 for each spring, if you want to think about it like this. Now, do I tell you the K? No, so now you do need to know the mass of the people and the mass of the compression of the car. So you do need it for this part. Okay, so you have the 4 people. They stand in the car. And the spring shrinks delta x. So the weight of the car plus the people should equal the force from the springs. The car is 2,000 plus 4 times 65 g equals 4k delta x, which is 0.015. So now we can get the k. So the K is very large, 369510. So I have my answer. T, is it the time to go up and down or just to go up? Let's see. Yeah. T is 0.23 of a second. Yeah. Got that? Nearly. Yes? Sorry? Yes? Okay. Let's close that. So, that was the last one, wasn't it?